Hello guys, let's talk about boiling point elevation. First, let's define what is the normal boiling point. It is the temperature at which the liquid's vapor pressure is going to equal to the atmospheric pressure, which is 1 atm or 760 torrs at sea level. When we have a solution made of non-volatile solutes and a solvent, it is going to be harder for the solvent to escape to the vapor phase due to the solute-solvent intermolecular interactions. So the vapor pressure of a solution is going to be lower than that of the pure solvent. And because the vapor pressure is lower for a solution, it is going to require a higher temperature to reach the atmospheric pressure. So overall, we are going to end up with a higher boiling point. And this higher boiling point is directly proportional to the concentration of the solute particles. So the change in boiling point or the boiling point elevation equals to the molality of the solute multiplied by K sub B, which is the boiling point elevation constant, and multiplied by I, which is the Van 't Hoff factor. And this factor just tells us how many numbers of particles we are going to get when a substance dissolves. Okay, and overall this equals to the boiling point of the solution minus the boiling point of the solvent. Okay, I hope this makes sense. Let's do a couple of sample problems. So here we need to figure out which of the following of 1 mole aqueous solutions will have the highest boiling point. So in order to get the highest boiling point, we need to achieve the highest change in temperature, so the highest boiling point elevation. As I said, it depends on the molality, which is going to be constant in this case, and on the boiling point elevation constant, K sub B, which is also a constant. So overall, in this example, the change in temperature going to depend only on I, which is the Van 't Hoff factor. So the number of particles a substance becomes when it dissolves. So let's try to figure out how many particles will we get when we take potassium sulfate and this dissolves. So when we have potassium sulfate, it's going to dissociate into 2 moles of K plus ions plus the sulfate ions. So that is going to give you 3 particles in total. What about potassium chloride right here? Well, it's going to dissociate into K plus Cl minus chloride ions. So in this case, I is going to equal to 2. What about glucose? Will it give us any ions? No, right? Because this is a molecular compound. So here I is going to equal to 1. What about iron 3 chloride? It's going to give us Fe3 plus 3 chloride ions. So I is going to equal to 1 plus 3, which is 4. Okay, what about aluminum sulfate right here? So I is going to equal to, we're going to have 2 of Al3 plus ions. And how many sulfate ions? 3, right? 3SO4, 2 minus ions. So the total of 2 plus 3 is going to be 5. What about potassium chromate right here? So we are going to get 2K plus CrO4 2 minus ions, chromate ions. So I equals to 2 plus 1, which is 3. So in which case do we have the highest Van 't Hoff factor? In case of aluminum sulfate, right? So this is going to mean that the highest boiling point is going to be achieved when we are going to have a 0.1 molar solution of aluminum sulfate, simply because it's going to give the largest number of particles when it dissolves in water. Okay, I hope this makes sense. Let's do another sample question. So here we need to figure out which of the following aqueous solutions will have the lowest boiling point. Okay, so we are trying to find the lowest change in temperatures. And we can see that we are given the molalities and also the compounds. So as in the previous case, delta TB, or the boiling point elevation, is going to depend on the Van Hoff factor, K sub B, which is a constant, and the molality. In this case, we need to take into account both I and M to figure out which of these solutions are going to have the lowest boiling point. So in the first case, we have 0.1 mole potassium sulfate. So I can just multiply these two values together and figure out how much the delta T is changing. So 0.1 mole multiplied by how many particles? 3, right? 2 from the potassium ions and 1 from the sulfate ions. So that is going to give us 0.3 molar. Okay, let's move on to 0.5 molar potassium chloride. So 0.5 molar multiplied by 2, right? Because we are going to have two particles, K plus Cl minus. So that is 1.0 molar for the KCl. How about 0.25 molar glucose solution? We're going to have only one particle, right? So 0.25 multiplied by 1 is going to give us 0.25 m. All right, let's move on. 0.15 mole iron 3 chloride. So 0.15 mole multiplied by how many particles? 4, right? 1 iron 3 plus and 3 Cl minus. So this is going to give us 0.6 molar. Then we move on to aluminum sulfate here. So 0.30 molar multiplied by how many particles? 5, right? So that is going to give us 1.5. And potassium chromate, 0.20 molar multiplied by how many particles? 3, right? So that is going to give us 0.6 molar. Okay, so now in which case we are going to have the smallest change in boiling point temperature? Did you find it? In case of glucose, right? Because when we multiply together the concentration times the number of particles the substance becomes when it dissolves, this is going to give us the lower number. So this is going to have the lowest boiling point. Okay, which one will have the highest boiling point? What do you think? The aluminum sulfate one, right? Because in that case, you are going to have the highest number when we multiply together the molality with the number of particles the substance becomes when it dissolves. So this would have the highest boiling point. All right, let's do another example. Here, we actually need to calculate the boiling point of a 1.8 molar potassium sulfate aqueous solution when the molar boiling point elevation constant of water is 0.51 Celsius per molality. So let's start first by figuring out the boiling point elevation using this formula right here. So delta T sub B equals to I, which is the Van Hoff constant. So we need to know how many particles will we have, and that is actually equals to 3, right? Because we are going to have 2 potassium ions and 1 sulfate ion as it dissolves in water. So 3 multiplied by K sub B, which is our constant right here, so 0.51 degrees Celsius divided by molality, and then that is multiplied by the molality, which is 1.8 mole. Okay, so if you do this calculation, you are going to get 2.75 degrees Celsius as the molarities cancel out. Now, this is the change in boiling point, and we know that we have a boiling point elevation. So the solution's boiling point is going to be higher than the boiling point of the solvent. What is the solvent in this case? Water. What is the boiling point of water? 100 degrees Celsius, right? So T sub B of the solvent itself is going to equal to 100.00 Celsius. And from there, we can calculate the T sub B of the solution, which is going to equal to T sub B of the solvent, which is 100 degrees Celsius plus the boiling point elevation, which is 2.75 degrees Celsius. So if you do this calculation, you are going to get 102.75 degrees Celsius. Okay, I hope this makes sense. See you in the next video.